The hypothesis test described in previous sections is a t-test for the mean of one population, but there are many other types of hypothesis tests. The t-test for the population mean is used in the common situation where the standard deviation or the variance of the population is not known. There's a slightly more accurate test called a z-test that can be used when the variance of the population is known. The general procedure for the z-test is the same as for other hypothesis tests. Start by identifying the null hypothesis, and then compute a p-value and interpret the p-value. For example, consider a test of the null hypothesis that the mean mu0 of the population is 1,000 and where the population has a known variance of 4. Here is a sample to use for testing the null hypothesis. A convenient test statistic is the mean of the sample minus the mean of the null hypothesis divided by the standard error SE of the sample mean, where SE is the square root of the known variance divided by the size n of the sample. This statistic is convenient because the sampling distribution is a normal distribution with a mean of 0 and a standard deviation of 1, which is the standard normal distribution. The traditional variable to use for this test statistic is z, and the resulting hypothesis test is called a z-test or sometimes a normal test. The p-value is the probability of the test statistic being as far or further from 0 than the test statistic for the sample. That probability is the area in the tails of the distribution, which can be computed using the cumulative density function CDF. This is also the result returned by the z-test function. The arguments in the z-test function are the sample, the known variance, and the mean mu0 under the null hypothesis. Usually the variance of the population is not known, however, so t-tests are much more common than z-tests. Returning to the t-test, in addition to testing the mean of one population, the t-test can also be used for comparing the means of two independent populations. For example, consider collecting samples from two populations and using those samples to determine whether the mean of the first population is equal to the mean of the second population. The null hypothesis is that the difference between the means of the populations is 0, and the alternative hypothesis is that this difference is not 0. Here's a paired histogram of the two samples, and these inputs give the means of the two samples. The mean of the first sample is bigger than the mean of the second sample, and the paired histogram does show that the distribution of values in the first sample is slightly above the distribution of values in the second sample. The question to be addressed with the hypothesis test is whether this difference is big enough to conclude that the means of the populations are not the same. A convenient test statistic to use here is given by this formula. Just as in computing a confidence interval for a difference of population means, the standard error is computed using the sizes n1 and n2 and the standard deviations s1 and s2 of the samples. The test statistic can then be computed using the sample means and that value of the standard error. As when computing the corresponding confidence interval, the sampling distribution of that test statistic is not a commonly tabulated distribution, but that sampling distribution is well approximated by a student t-distribution with an effective number of degrees of freedom given by this formula. Here's a plot of the student t-distribution with that number of degrees of freedom and with the test statistic shown on the plot. The p-value is the area in the tails of that curve, which can be calculated using the CDF function. This is also the calculation that is programmed into the t-test function, which gives the same result. This p-value is about 7.8%, which means that there is a 7.8% chance of getting a difference of sample means that is as big or bigger than the difference between the means of the two collected samples, even if the null hypothesis is correct. This p-value can be interpreted by choosing a level of significance alpha and comparing the p-value with alpha equals 5%, for example, and p-value of 7.8%, the conclusion is that the null hypothesis is not rejected, since the p-value is bigger than alpha.